Hello, everyone. I'm excited to be part of this conference, the 4th International Symposium on Computer Science, Digital Economy, and Intelligent Systems, CSD 2022, holding here at China. My name is John Efio, and I'll be presenting the report of our research on CyberSCADA network security analysis model for intrusion detection systems in a smart grid. This research was carried out by myself with Dr. Bodunde Akiyemi, Professor Emmanuel Lajibu, Professor Ganiyu Aderamo, and Professor Jules Degila. Myself, Akiyemi, Lajibu, and Aderamo of the Department of Computer Science and Engineering, Bafemi Awolowo University, Nigeria, while Professor Jules Degila is of the Department of Computer Science at the African Center of Excellence in Mathematical Sciences, Information and Applications of the University of Bome Calavi in the Republic of Benin. So it's a joint project. This is the outline I'll follow for this presentation. I'll take us through a brief introduction, then we'll look at cyber attack modeling, the method we adopted, the data set that we used, the experimental setup, results, conclusion, and then the references. Introduction. The smart grid is a highly dynamic and critical domain that requires great attention in all phases of its operation. Basically, the smart grid has 4 major phases. The first phase is the phase of power generation from the power plants. Then it moves down to power transmission, to distribution, and then consumption by the customers. Now, all of these operations, all of these phases are controlled by some systems, some industry-specific systems, which are generally referred to as industrial control systems. So, and chief of these control systems or industrial control systems is the SCADA. SCADA is supervisory control and data acquisition system. Basically, what it does is to supervise the processes and control data acquisition. And is also able to control other components of the smart grid network, like the programmable logic controllers, the PLC, remote terminal units, circuit breakers, and other sensors and actuators that form parts of the smart grid network. The current design of enterprise networks and the Internet of Things has included the ones isolated SCADA systems into the corporate network architecture. Basically, SCADA systems were designed to be standalone systems. They were not parts of the corporate network, as it were. But because of the advent of IoT, sensors have been introduced, and then SCADA systems and the components have been integrated into the corporate network. So these has positive sides and negative implications for cybersecurity reasons. Basically, for the gains, the pros of the convergence of the operational technologies, talking about the operations of the SCADA systems and all the components, provides remote access and management of equipment, systems and internet on data via IP infrastructure. And also, one can easily have access to cloud storage and other services. But it's also the advantage of easy data acquisition through remote sensors, support for interoperability of legacy systems with IP systems, and other benefits that come with the integration or the fusion of the SCADA systems with the enterprise network. And on the negative side, this fusion creates sort of unrestricted backdoors through enterprise networks into the critical domain. Basically because the SCADA systems, like I've said before, were isolated systems. For that reason, security mechanisms were not parts of the protocols design. They were not part of the architecture. So with this fusion now, the SCADA systems have become easy targets or sub-targets for cyber attacks. Stateful cyber attacks on the SCADA systems can have very devastating impacts on the business chain in terms of loss of financial assets and lives, especially for the smart grid, like what happened in December 2015 on the Ukrainian power grid, where Black Energy 3 attack was launched, and over 225 customers experienced a blackout for over 3 hours. And also the crash override attack in December 2016. These are some of the attacks on smart grids that have crippled the smart grid networks for us and have resulted in so many vital incidents. Specifically, breaches on a CyberSCADA system in the smart grid will result in information and financial loss, operational disruption, danger to lives of the personnel, sabotage of power plants, damaged equipment, and other forms of dangers that such a thing can lead to. Intrusion detection systems, IDS, are important in identifying abnormal behaviors or patterns in network traffic to constantly put the networks on a check against attacks. There are quite a number of intrusion detection systems that have been developed over time. Some traditional, some have leveraged some level of intelligence from machine learning algorithms. So machine learning algorithms are capable of increasing the intelligence of intrusion detection systems to ensure timely and accurate intrusion detection for prompt countermeasures development. However, not all machine learning algorithms are suitable for developing appropriate models for all problem domains and datasets. So there is a need for these algorithms to be tested to identify which ones are suitable for each application domain or each data set available that is to be modeled, or kind of attack that is to be modeled. So this paper evaluates 6 traditional machine learning algorithms. We have evaluated the k-nearest neighbor, support vector machine, decision tree, logistic regression, random forests, and the Gaussian bias to identify the most suitable classifiers that can be used to develop intrusion detection system and models for smart grid mission critical networks. So our major contributions in the work or in the research or study has been that we have examined the existing body of knowledge on the problem to establish the need for this study. We've applied principal component analysis to select valuable features of a smart grid data set. We've used 3 ensemble classifiers, basically data boost, gradient boost, and the XG boost to boost the feature extraction process. We leveraged supervised learning algorithms to predict intrusions on smart grid, validated the models, and measured the performance with suitable metrics to aid cybersecurity intrusion detection systems, attack analysis, and in the problem domain, basically in the smart grid. So looking at the attack modeling, cyber attacks have been generally modeled in literature using the risk characteristic model, dynamic model, or the component-based model. In the risk-based modeling, the characteristics of the risk involved in cyber attacks are used to compute the degree of severity of successful attacks on the system being modeled. So equation 1 represents the risk characteristic model, which we used, where I subscript S of F is the system's risk, I subscript M is the impact of the risk, and LH of F is the likelihood of a given failure F. The likelihood of the failure is dependent of the system vulnerabilities and threats. So we have modified, according to the work of the author cited in number 30, the equation 1 has been modified to give you equation 2, where the likelihood of vulnerabilities has been introduced, which is V of F, and then the likelihood of the threats with respect to failure, T of F, has been introduced into the equation. So an author has observed that equations 1 and 2 depend on historical data for implementation. So, and the absence of such will make the model unrealistic for modeling. However, it's still applicable to the problem we are modeling. So for the dynamic system based model, it's a representation of the physical processes in the smart grid. So these physical processes are modeled as vectors, as attack vectors. We can see we use equation 3 for the modeling. Right, this helps to explain the time evolution of the system state Z, as you can see in the equation. So Z is given as the time derivative of a small z and c, where c is the input factor, but is employed to establish the degree of attack severity and compute the total time for detection of threats. So for the data sets that we used for our experiment, the Oak Ridge National Laboratories of the Mississippi State University have set up a power system testbed and generated some data set which we've used. The testbed ran 2 generators, which were named as G1 and G2, with some intelligent electronic devices, 4 relays, 4 circuit breakers, 3 bus to line communication system. So 37 events for each of the data sets. Basically, 3 categories of data sets were generated. They generated the binary class, they generated the triple class, and they also generated the multi-class. All right, so and 37 events or scenarios were modeled or were generated or experimented in the data sets. So the data set contains standard measurements of electric transmission systems with the disturbance, control, and cyber attack behaviors, which obviously are the abnormal traffic. So these measurements are readings of synchrophasor and data logs, basically from syslog, snots, simulated control panel, and relays. So the 37 scenarios were subgrouped into natural events, which were 8 in number, no events, 1, and attack event 28. This study used the 6th category of the binary data class that we talked about, and then the 3 class for training and testing the models. So we basically use 2,484 samples with 67 features, while the 3 class contain 4,967 instances with 129 attributes. Experimental setup. We developed a model using Python on Google Colab, which makes it easy for sharing, for group contribution and all of that. The principal components analysis and free ensemble methods were used for feature extraction. Machine learning algorithms implemented were, as I've mentioned before, the Gaussian F-bias, decision tree, random forest, logistic regression, support vector machine and kernels. And the metrics used for evaluation were accuracy, F1 score, recall precision, root mean square error, and detection rate. So table 1 gives us the result of the gradient boosting learning rates. We used 7 learning rates to experiment the gradient boosting, starting from 0.05 up to 1 for training and validation sets. We noticed that the learning rate of 0.75 give us the best outputs for both the training sets and the validation sets, and that was closely followed by learning rates of 1. So the learning rates of 0.75 was eventually used for the training of the gradient boosts, boosting classifier. So table 2 gives us the results of the feature structure classification for the ensemble methods. So here, the 3 ensemble methods returned same results for all the metrics: accuracy, precision, recall, and F1 score. So other boost, gradient boost, and XG boost returned 99%, showing very high outstanding performance. And then the table 3, where we have the model classification results for the 6 traditional machine learning algorithms that were they were implemented. So we have the accuracy, precision, recall, F1 score, and detection rates. So it's important for us to report that decision tree give the best basically decision tree and k-nearest neighbor returned the best results of similar values for accuracy, precision, recall, and F1 score. However, when it comes to detection rates, the Gaussian naive Bayes return the highest detection rates, followed by the k-nearest neighbor in this model that we reviewed. And table 4 is a cross-validation results for the algorithms. Here we saw that random forest gave 100% accuracy for cross-validation. That was followed by decision tree having 99, and then k-nearest neighbor having 98%. So we also performed ROC random cutoff, which we have the results presented in table 5. So here we noticed that k-nearest neighbor and random forest had the best results of 99%, closely followed by the decision tree having 96%, and logistic regression having 95%. So we have figures of the ROC random curve. So figure 1 is the output for random forest, and then figure 2 is the output for logistic regression. You can see the performance for random forests going very close to 100, and then you can see the logistic regression. And then figure 3 is the output for decision tree, very close to 100 as well. Yeah, that's above 90. And then the k-nearest neighbor can see the performance. And then for the Gaussian naive Bayes, you can also see the ROC random curve outputs. So the summary of our results. During the feature selection process with principal components analysis, the first principal component was found to be of greatest importance in the data sets, and a 2% loss of information from the components analyzed was observed. Basically, from the explained variance ratio, PC1 held 85% of the information, followed by PC2 with 12. Of course, the margin is wide, while the rest were insignificant. This shows that PCA offers a good technique for feature selection in the power line critical networks. So 3 ensemble methods that were further used for boosting. In the gradient boost classifier, like I reported earlier, the 7 learning rates were experimented to determine the accuracy score on the output was follows. So we found out that 0.75 learning rates was better for both training accuracy and validation accuracy, and was thus used for the experiments, as we've reported in table 2. So with that done, the root mean square of the XG boost score was reasonably low, which was 0.24 with the accuracy score of 99%. Comparing the metrics of the 3 ensemble classifiers for feature extraction, we noticed that all performed equally higher, having 99% on all the indices. Accuracy, precision, recall, and F1 score as also reported in table 2. In model selection, we used a k-nearest neighbor decision tree, and all on the rest, making 6 of them. We noticed that k-nearest neighbor on decision tree had the highest accuracy, highest precision, highest recall, and highest F1 score of 99%. That was uniform for the 3 of them, for the 2 of them. That seemed to be consistent throughout the classification process. We've reported that in table 3. And then the random forests, on the other hand, performed significantly poorly. We further computed the detection rates for comparison of the models from table 5. The quotient net bias classifier has the highest detection rates of 99%, with a false positive rates of 0.1 for that type vector. In comparison, random forest has the highest true negative rates of 98% for normal events, with a false positive rates of 0.5. So the random forest classifier appears to have the best ROC curve since it ranks all positive above all negatives with the AUC of 1.0. This is closely followed by the gain nearest neighbors, Gaussian bias, and the decision tree classifier. So these were the things we noticed in our experiments and we have presented. So conclusion, this paper has demonstrated various machine learning algorithms to aid intrusion detection, analysis in the CyberSCADA networks. Ensemble classifiers such as Data Boost, Gradient Boost, and XG Boost have been validated and found to be efficient in and very significant and helpful in boosting machine learning algorithms for feature extraction in data sets such as the one used in the study. The learning rates of 0.75 is good for gradient boost classification boosting based on our experiment. Decision tree and care neighbors are consistently relevant as they return high results of the metrics used for evaluation and validation. The detection rate of the Gaussian bias network was found to be high, with significantly low false positive rates. Selecting appropriate machine learning algorithm for data processing, feature extraction, and model selection will play a significant role in model building and deployment. As we are aware, an intrusion detection model is expected to have as significantly low false positives as possible, as well as the root mean square error. This study has provided useful insights in selecting and building models with low false positive rates while improving detection rates. So we hope that further study will explore other ensemble algorithms and unsupervised techniques as may be appropriate for the scenario under investigation. Basically, this study has helped to understand the fact that there is need for intrusion detection system to improve its intelligence, especially for the smart grid, because any successful attack can cause so much danger to the systems, to lives, to properties, and even phones and all of that. So this is what this study has given an insight into. So I hope you have enjoyed my presentation. Thank you for listening. So I'll be waiting to take some questions. Thank you. So these are the references that I want to look at.